So the first factor we want to look at among the things that affect the SN2 and SN1 reaction rate is the ability of the leaving group to leave. And simply put, leaving group ability follows exactly the same trend as acidity. The more stable the anion, the better the leaving group. So if we know our acid strength trends, we can say that good leaving groups are the conjugate bases of strong acids. And the strong acids are the acids with negative pKa's. So all we need to do in order to understand leaving group ability is understand acidity. If we know what causes an acid to be a strong acid, to have a negative pKa, we can determine which are the stable anions that are going to turn out to be good leaving groups. And most of the leaving groups that we're going to be using fall into two categories. They are either halide ions, chloride, bromide, and iodide, which are the conjugate bases of Cl, HBr, and HI, respectively, which we know have pKa values of -8, -9, -10. And those anions are very stable because they are highly polarizable. Since iodine is slightly larger than bromine and bromine is slightly larger than chlorine, the acid strength increases as we go down the series, and the anion stability increases as we go down the series. Fluoride ion is not a good leaving group, because HF is not a strong acid. HF has a pKa closer to 3, not -3, but 3. And it's not a strong acid. So fluoride is a poor leaving group and will not participate in nucleophilic alkyl substitution reactions. Which doesn't mean I won't try to get you to make fluoride leave on the quiz. But you shouldn't let me fool you. If you see fluoride, the correct answer is no reaction. Fluoride is not leaving. Chloride, bromide, and iodide leave because their conjugate acids have highly negative pKa values, highly polarizable, stable anions. The other class of leaving groups that's going to be important are sulfonic acid groups. A sulfonic acid is similar to sulfuric acid. We know sulfuric acid is a strong acid. The difference being in a sulfonic acid, one of these OH groups has been replaced with a carbon. So for example, the methane sulfonate ion. And is abbreviated NS. So methane sulfonate is a good leaving group. Another one that's important, it's used very frequently, is para-toluene sulfonate. Called tosylate and is abbreviated TS, where we have a toluene group. Methylbenzene is toluene. The para position is from the sulfonic acid. The trifluoromethane sulfonate ion triflate and is abbreviated TF. All of these anions, like the hydrogen sulfate ion, which is the conjugate base of sulfuric acid, are resonance stabilized. And the sulfonic acids tend to have pKa values -3, -1 to -3-ish. Triflate being a little bit better because the highly electronegative fluorine atoms remove electron density and stabilize the negative charge, not just by resonance, but also by what we call an inductive effect. So really, your job is fairly simple when you're trying to determine if there's a leaving group present that's good enough to leave. You'll either see chloride, tosylate, or triflate. Those are the 6 leaving groups that you'll see very commonly in this course. There are others, because you could put many other things here attached to the sulfur rather than methyl, trifluoromethyl, or the para-toluene group. And you may see them in some cases. But what you're going to be looking at is an S doubly bonded to 2 different oxygens that allows resonance stabilization for the oxygen. But organic nitrates tend not to be very stable. Perchloric acid, but organic perchlorates are explosive, so we try to avoid combining perchloric acid and organic materials. Chloric acid is just not very common. And so pretty much it's going to be sulfonic acid derivatives and halide ions that we're using for our leaving groups. And it's convenient that alcohols can readily be converted into the corresponding sulfonic acid derivatives by reacting a sulfonyl chloride with the alcohol. So if we have an alcohol, we know that hydroxide is a terrible leaving group. Conjugate base of hydroxide is water, which has a pKa of 15, so there's no way hydroxide ion is ever leaving in a nucleophilic alkyl substitution. But if we react that with trifluoromethane sulfonyl chloride in the presence of a base, often triethylamine, we can do a nucleophilic acyl substitution and replace the hydrogen and take this chlorine off of there and replace it with this group, liberating HCl. The amine reacts with the HCl and speeds that reaction along, and we have taken a bad leaving group, hydroxide, and converted it into a good leaving group, the methane sulfate group. So that's very convenient, and we'll see this mechanism later.